Okay, so before we dive into Unit 3, a couple of scheduling notes I want to make. So the next 3 weeks basically. So it looks like this Friday, that would be March 10th. Looks like Mauston, you guys are not in session. And then on Monday, which is what, March 13th, and we have both Clayton and Flambeau. They're scheduled to be out of session. Clayton, I know your schedule has changed around, so I'm not sure if that's still a day off for you or not on Monday. But so what I'm going to do is, since between those 2 days, each of the schools is out, Friday and Monday will be the same lecture. So that way, Mauston, on Friday, you won't have to log in from home. We'll repeat that same lecture on Monday for you when you guys are back in school. Clayton and Flambeau, you guys won't have to try to log in that Monday from home because it'll just be the same lecture that you will all have seen on Friday. Then after that, Wednesday, March 15th, and Friday, March 17th, it looks like Flambeau is still out of school. You got your spring break a week before ours. But we are going to have class as normal those 2 days. Just because there's material I have to cover, so the videos will be available if you're not able to log in from home. I see you're not here this morning right now, but hopefully you'll see this video and you'll get that message. You'll have to find some way to log in from home or watch the videos later for March 15th and 17th if that's your spring break. And then March 20th through 24th is my spring break, so there is no class that week. And I will send out an email to your contact people at the school explaining all this as well, so that they know what's going on. I realize that some school schedules has changed, but I know Flambeau is definitely out all of next week for their spring break. So we'll do this to kind of keep everybody in the loop and to stay on schedule. I have one flex day, that's why I'm able to repeat that lecture Friday and Monday this coming week so that nobody has to log in from home on those 2 days. So anyway, we had our test last class, so today we start Unit 3. And as I mentioned before, Unit 3 is really the heart and soul of this course. It's where all of our dosage calculations come in. It's really the purpose of this class. All the other stuff, Units 1 and 2 were preparation to make sure we had the background knowledge for this unit. Units 4 and 5 coming up later are things that we had to put in to make this prepping for anybody who is going on to a bachelor's degree, prepping them for those next courses, that college algebra course and the statistics course. But the next few weeks, about 4 or 5 weeks, what we're going to be doing here in this unit is really what this class is all about. And that, of course, is our dosage calculations. And as I mentioned, this is the part of the course where students hit stuff. Most of what we do is going to use concepts that you have seen before, but in ways that you have never used them before. So this is the part where students start to see that it's not the easy class it looked like for the first 2 units. So please bear with me and make sure you are going through the homework a little more carefully and a little more detail for this unit. So some of the basic concepts that we have studied so far that are going to be used in this unit, one of the big ones is dimensional analysis. And dimensional analysis was what we used for measurement conversions. If we had 2 fluid ounces, and I need to know how many milliliters that is. Well, we have to look for an equivalency that says 1 fluid ounce is 30 milliliters. Now, this is the one that I said, depending on where you looked it up, might be 30, might be 29.9. 30 is close enough. And so then we took our 2 fluid ounces and we made it into a fraction. Put it in over 1. And then we use that equivalency as a conversion factor. We're getting rid of fluid ounces, so we put fluid ounces on bottom. Going into milliliters, 1 fluid ounce was 30 milliliters. The fluid ounces canceled out. 2 times 30 milliliters was 60 milliliters. Over 1, so just 60 milliliters. Dimensional analysis has a deeper application, though. We might have, let's say, an IV set at a flow rate of 480 milliliters per hour. And on the label of the medication, it states that that medication is constituted as 12 milligrams in 5 milliliters. So our dimensional analysis tells us how much medication that patient is actually receiving. We can take that 480 milliliters per hour, and remember, a rate like that, a unit rate, is really 480 milliliters over 1 hour. We need it in that form to calculate it with. And then we have this equivalency here. It looks like it is a rate, but every rate is also an equivalency. 12 milligrams in 5 milliliters is saying that 12 milligrams of medication is equivalent to 5 milliliters of the solution. So we want to get rid of the milliliters, so I'm going to put milliliters on bottom. And I want to go to milligrams. 12 milligrams is 5 milliliters. And the milliliters cross cancel out. We have 480 times 12 milligrams. I believe that's 5670, but I'm going to double check that. 5760, thank you. Milligrams. Over 1 hour times 5 is 5 hours. And then we have to divide that out. We divide both the top and bottom by 5. Of course, 5 hours divided by 5 is just 1 hour. 5,760 divided by 5 is 1,152 milligrams. So that is 1,152 milligrams per hour of that medication if they're receiving 480 milliliters per hour of solution. Another big tool we looked at is a ratio and proportion. And the part that I want to look at here is, well, let's look at a simple ratio. Let's look at students, a comparison of students in the high school class, that's you guys, to students in the tech class. So right now we're actually down to 6 students in the high school class and 18 in my tech class. This gives me a total of 24 students. Now, why did I want that total? Well, because there are a couple of ways we could express ratios from this. We could express the ratio as 6 to 18, which is basically, 6 over 18 is a fraction like that. But the wording is important. That's just comparing the 6 in high school to the 18 in the tech class. But another wording that's what's going to be more applicable to what we're going to do in here would be to write it, instead of 6 to 18, is compare the high school students, all of you, to the total. where we'd say 6 out of 24 students in the class are in high school. So that 6 out of 24, another way that could be worded would be 6 in 24. It is implying that this 6 is part of the 24. So when I have that ratio, 6 in 24, in this case, because I know there's only two groups, there's high school students and there's the tech college students. 6 and 24 are high school. Well, then it implies I can find 24 minus 6, or 18 in 24, are tech students. And so that relationship of the two parts coming together to make the whole allows us to make those two different ratios. The reason that's so important is one of the first major topics we're going to discuss in our dosage calculations this unit is the concept of a dilution. And a dilution is just a form of a mixing ratio. And there's two ingredients that are going to be mixed. The first one is some sort of concentrated substance. That could be a medication. It could be an antiseptic, a cleaner. It could just be some sort of a supplement. Maybe vitamin C or vitamin D, or even just electrolytes going through an IV. Or it could be a solution of any of those, just a more concentrated form of a solution than any of those. So it may not even be a pure substance. It could be one of those substances already diluted down. Now, since we have any of those substances could be, remember we referred to this as our active ingredient. And I mentioned this word before. The word we're going to use to describe these in this class, for the rest of this class, is serum. So when I use the term serum, just as a generic term, it could be a medication, an antiseptic, a supplement, a vitamin, or just even the more concentrated form of a solution before we dilute it. So a dilution is, the purpose of a dilution is to reduce the concentration, either taking it from a pure substance down to a diluted substance, or a concentrated solution to a less concentrated solution. Then the next thing we have, the second part, is a vehicle. And a vehicle is typically some sort of sterile water. What the vehicle does is it carries the serum into the patient. If we have a powdered pain reliever, can't just give them the powder. Either has to go into a capsule, that can be a vehicle, or into a solution if we're talking about IVs, so it can be injected into the bloodstream. And so, like I said, this is usually some sort of sterile water. And the sterile water used, it could be something called normal saline. Normal saline or normalized saline is just a saline that has been pH balanced. It's sterile water with some electrolytes put into it, so it balances the pH, it matches the pH of the human body. Or it can be some other substance that's not necessarily just water, but it's a neutral, isn't there? A neutral solution. So it has no active ingredient, no medicinal value to it at all. Its only purpose is to carry that serum into the patient. Well, notice that both of those have the abbreviation, the initials NS. So in this course, when I refer to NS, that's what I'm talking about, is either normal saline, neutral solution, some form of sterile water. So in a dilution, it is a ratio of a concentrate to a total solution. So if I have a 1:6 dilution, what that is saying is we have a ratio of 1 part serum, the concentrate, to 6 parts of total solution. So that term parts, that just means it's the same units from one to the other. That could be milliliters, could be milligrams, could be fluid ounces, some unit of measurement that is consistent between the two substances. So let's break this down a bit. If I tell you we have 120 milliliters of a 2N5 iodine solution. What that is saying, the 2N5 is our ratio. Remember, the 2 represents the serum. In this case, that's the iodine. And the 5 represents the total solution. If I want to know how much iodine is in the solution, I can just use this ratio here. 120 milliliters of the 2N5 dilution. That is indicating that 120 milliliters is the total solution. I put 120 milliliters on bottom. And if I cross multiply and divide here, 2 times 120 divided by 5 gives me 48. The units have to be the same, milliliters. That is of iodine. Now, if I want to get how much saline is in here, how much NS is in here, I have 2 options. I can either subtract here, 120 milliliters total solution minus 48 milliliters iodine or serum gives us 72 milliliters of NS, of neutral solution, normal saline. Or I could do what we did with the students up above. If 2 of the total of 5 parts is serum, 5 minus 2 would be 3 parts out of the 5 total that are the NS. So the 5 parts is still the total. It's just we subtracted the 2 parts of serum from that total to get the other 3 parts are that neutral solution of some sort. And then, of course, on the other side of that, we have our 120 milliliters of total solution, and we cross multiply and divide. 3 times 120 divided by 5 is 72 milliliters. So 72 milliliters of our sterile water. So here we were able to find the serum given the total. We were able to find the amount of sterile water given the total. Let's look at an example of how much 3N8 heparin solution can be created using, let's go 48 milliliters of heparin. So here again, our dilution is 3N8. Remember, the 3 represents the serum. In this case, that's the heparin. And the 8 represents the total solution. And I'm just going to start writing total for that. In this case, what we know is 48 milliliters of heparin. So that goes with the 3, so that goes on top. Are we looking for the total? Well, yeah, how much of that 3 and 8 dilution can be made? So what we're looking for is the total. So it'll just be that bottom number. So we cross multiply and divide. 8 times 48 divided by 3 is 128 milliliters. So we can create 128 milliliters of that 3 and 8 dilution of a heparin solution using the 48 milliliters of heparin. Or we might ask, how much NS is required to create .400 milliliters of a 3 in 10 dilution? So here again, we have our dilution is 3 in 10. But if we look at it, the 3 is the serum. We didn't specify what the serum is here, but it doesn't matter. 10 is the total solution. Well, we have 400 milliliters. That does represent the total solution. But what I'm looking for is not the serum. I'm looking for the NS, the other part of it. Now, I could find the serum and subtract, but it's better form to find the ratio of NS to total and use that. So we still have 10 total parts here of solution. The NS is the 10 total minus the 3 parts of serum, giving us 7 parts is sterile water. And now we can compare that to the total of 400 milliliters. We'll cross, multiply, and divide. 7 times 400 divided by 10 gives us 200 milliliters of NS, or normal saline, that would be required to create that dilution. Or we can look at it from the other side. How much of a 2 in 7 dilution can be created using 150 milliliters of NS. So again here, we have our dilution. This is a 2 in 7. Once again, the 2 represents the amount of serum, and the 7 represents the total solution. We don't have either of those numbers. We have the amount of saline. So we need to adjust this again to a ratio of saline to total. So the total is still going to be 7. That doesn't change. The saline will be the total of 7 minus the 2 parts serum will give us 5 parts of saline. And now we can set up the rest of our proportion. We have 150 milliliters of saline. To find our total, we'll cross, multiply, and divide. So 7 times 150 divided by 5 gives us 210 milliliters of that dilution that can be created using the 150 milliliters of saline. We might ask how much saline should be mixed with 80 milliliters of serum to create a 4:9 dilution. So again, let's look at our dilution. We have 4 and 9 as a 4 to 9. The 4, once again, represents the amount of serum, and the 9 represents the total solution. Well, we have the serum, we have the 80 milliliters of serum, but we're not looking for the total. We're looking for how much saline. Now, once again, here we could just put in the 80 milliliters, cross, multiply, and divide to get the total, and we could subtract to get the saline. But let's go ahead and redo our ratio here. And the ratio we want is the ratio of serum to saline. So if the amount of serum is still 4 parts, that hasn't changed, the amount of saline will be the total of 9 minus the 4-part serum, which will be 5 parts of saline. So I have a ratio of 4 to 5, ratio of serum to saline. And now I can put in the 80 milliliters of serum and cross multiply and divide. 5 times 80 divided by 4 would be 100 milliliters of saline required to make that dilution. And we can go from the other side of it as well. How much serum should be mixed with 120 milliliters of saline to create 120 milliliters of NS to create a 1:9 dilution. So again, our dilution of 1:9 is just a starting point. The 1 is the serum. That is what we're looking for, is the serum, but the 9 is the total solution. We're not looking for the total solution. We don't have the amount of the total solution. So we need to adjust this to be a ratio of serum to saline. Well, once again, our total part serum doesn't change. It's still 1 part. The amount of saline, our neutral solution, is the total parts of 9 minus the 1 part serum, gives us 8 parts of saline. So our ratio of serum to saline is 1 to 8. We know that I have 120 milliliters of saline, so the 120 milliliters goes on bottom, and now we can cross, multiply, and divide to find the serum. So 1 times 120 divided by 8 gives me 15 milliliters of serum that should be combined with that 120 milliliters of saline. So the one direction we haven't gone yet is actually finding the dilution. We might ask, find the dilution created if 60 milliliters of serum is dissolved into, let's do 150 milliliters of total solution. So this one's pretty straightforward. Our serum to total is the dilution. Well, the amount of serum we have is the 60 milliliters. Total solution is the 150 milliliters. So here the milliliters will cancel out. Units, just like any other ratio, the units disappear. Both 60 and 150, they can both be divided by 10 because they end in 0. So let's do that first. 60 divided by 10 is 6. 150 divided by 10 is 15. Both of those can still be divided by 3. 6 divided by 3 is 2. 15 divided by 3 is 5. So 2 to 5, or a 2 in 5 dilution. Well, more common than that is to say, find the dilution created if 40 milliliters of serum is combined with 140 milliliters of saline. So now again, our dilution is serum to total solution. We have the serum, 40 milliliters. So put 40 milliliters on top. The total solution is not just the 140 milliliters of saline, it's the 140 milliliters of saline plus the 40 milliliters of serum that we have on top. So this comes out, the milliliters are going to cancel out anyway. This comes out to be 40 over 140 plus 40 is 180. Both of those numbers can be divided by 20. 40 divided by 20 is 2. 180 divided by 20 is 9. So 2 to 9, or 2 in 9 dilution is what's created there. So we have to be very careful when we're looking at these dilutions to make sure that if we're given the saline, that we add the serum to that to get the total amount of solution. Some of the examples we do, in fact, we'll do a couple of examples right now where it's very important to have that accurate dilution. One place where a dilution is used, we'll look at later on, we'll look at using a dilution to reduce the concentration of a medication. But one of the ways it's used is in lab testing. Meters have a limit, like a blood sugar meter has a limit of 1,000 milligrams per deciliter of blood glucose in the blood. So let's say the meter limit is exceeded. We test a sample of blood and we get an error. So it's telling us that the level is above that limit of 1,000 milligrams per milliliter. So that means, first of all, that's a bad thing. That's very high already. But it means we need to do something to be able to get an accurate reading. So let's say we use the blood to form a 2 in 5 dilution. So we combine it with the neutral solution or sterile water to dilute the blood down. And we get a diluted reading of 411 milligrams per deciliter in that diluted solution. So how do we find the true reading? Well, the true reading is going to be bigger than the diluted reading. To find the true reading, we use this dilution ratio. It's a 2 in 5 ratio, so it's 2 to 5. Over here, we have the diluted amount. The diluted reading goes with the smaller number, and the true reading will go with the larger number. So the diluted reading was the 411 milligrams per deciliter. And we just cross multiply and divide. 5 times 411 divided by 2 gives us 1,027.5. Of course, that's milligrams per deciliter. So there is our estimated true reading. Why do I say estimated? Well, because when we do this dilution, there's an increase in the error. Let's say that the meter is a plus or minus 4%. Well, after performing this dilution, we have increased that error. Because we've diluted it, that with a 2 to 5 dilution, the change in error is the same. 5 times 4 divided by 2, that becomes a 10%, plus or minus 10% error now in that diluted, because of the diluted reading. Or let's say we have, again, another situation where the meter is exceeded. And so we mix 400 microliters of urine with, let's see, 5 milliliters of NS. We get a diluted reading of 98 milligrams per deciliter. Let's find the true reading. Well, to find the true reading here, first thing we need to know is we need to know the dilution. So here the serum is going to be the urine. That's 400 microliters. Now I use the medical abbreviation MCL, but remember there's also the abbreviation microliters like that. Over, now here's where we have to remember, it's the 5 milliliters of saline plus the 400 microliters of the urine. So the first thing we have to do is we have to change microliters into milliliters. 400 microliters is 0.4 milliliters. So then we have 5 milliliters plus 0.4 milliliters for our total. So this is going to be 0.4. The milliliters are going to cross cancel out, or going to cancel out, over 5.4. Now what I'm going to do here is a little bit of a trick. I'm going to divide by the 0.4. The reason I'm dividing by 0.4 is I want to get this number here to 1. So 0.4 divided by 0.4 is just going to be 1. 5.4 divided by 0.4 is 13.5. Well, that's still not really a true dilution. I'm going to multiply both of those by 2 to get a 2 in 27 dilution. So now that I know my dilution is 2 in 27. Now, realistically, I could have used the 0.4 over 5.4. It would work. We just typically like to get our dilutions into whole numbers. So it's a 2 in 27 dilution. Our diluted reading is 98 milligrams per deciliter, and we cross multiply and divide. So we do 27 times 98 divided by 2 gives us 1,323 milligrams per deciliter. If we had used the 0.4 over 5.4, we would have had the same result. It would have just been 5.4 times 98 divided by 0.4, giving us that same 1323. So why do we prefer to have the dilution is whole numbers 2 to 27? Because remember, we said the error in that meter increases as well by that dilution. So we wanted to, this gives us an idea that whatever our plus or minus is, our error is in that meter, it's going to be 13.5 times, or a 2 to 27 ratio of that error. Where is this, other applications of this? Well, one of the things we want to be able to do is we want to change the concentration of a solution. We want to dilute a solution. So let's say remember we had our solution concentration formula where we looked at the amount of serum or active ingredient was equal to the concentration. Now remember, that's just a rate form or decimal form of a percent times the total volume of the solution. So let's say we ask how much saline is needed to dilute 240 milliliters of 12% solution to 8%. So we're going to start out with what we have. We have 12%, so that's 0.12, and we have 240 milliliters of it. If we multiply that out, 0.12 times 12, 0.12 times 240, I should say, gives us 28.8 milliliters of serum in that original solution. Well, we want to keep the 28.8 milliliters. We're not adding any serum here. We're simply adding saline to this. So we want to then change this concentration to 8%, so that's 0.08, and we want to figure out what that new volume will be. Well, to find that new volume, we divide by 0.08. I believe that gives us 360. It does. So we need 360 milliliters of total solution. Well, we had 240. So 360 milliliters minus 240 milliliters gives us that we need 120 milliliters of saline to make that dilution. Or we could look at it in terms of a dilution itself. The dilution itself, we started out with 240 milliliters of the concentrated solution. Now that's the 12% solution here. We ended up with 360 milliliters of the diluted solution. Milliliters cancel out. And I know we're running out of time, so I'll do this rather than step by step. I'll reduce it all to once. That's 2 to 3. So it's a 2 and 3 dilution to dilute that from 12% to 8%. One of the things we'll look at this Friday is the shortcut for doing that. Now remember, like I said, Boston, you guys are scheduled to be off on Friday, and Clayton and Flambeau are both scheduled to be off on Monday. So what I'm going to do is, so you don't have to log in from home those days, I'm going to repeat the lecture. So the lecture I do this Friday will be repeated on Monday. So Boston, you don't have to worry about logging in from home on Friday. You do have homework out of the book, page 130 through 132, 1 through 37, the odds. Like I said, this is where students start to struggle a little bit because this is stuff you haven't seen before. So make sure you definitely do some of the word problems, but also do a good share of the other problems as well. With that, you guys have a great day. We'll see some of you on Friday and the rest of you next Monday.